Hello and welcome back, G-Man in the Studio Lab. Today I'll continue my introductory series of videos covering modular synthesis. Let's dive into the world of oscillators, what they do, how to patch them, and a few tips and tricks. I'll explore a few different kinds of oscillators, but first a quick recap. The oscillator is the first block in our typical synth patch. It's responsible for generating raw audio sound. We are interested in oscillators that can take control voltages from other modules as well. You know it as the VCO, the voltage controlled oscillator. Let's get started. Here I have my 4027 VCO, a simple oscillator with some basic features. First I'll plug the sine wave output into an oscilloscope module. It can show me what the waveform looks like. Then I'll run the signal to an output module so we can also hear it. I can sweep the pitch using the frequency control. The sine waveform is clean and pure, but we have other waveforms available. Just move the patch cable to other waveforms to see what they sound like. The next one is triangle. Pretty simple like the sine wave, but a few more harmonics. The sawtooth is yet more harmonics and has a buzzy quality. Last there is the pulse wave. It sounds more hollow or witty. The pulse wave has some extra features that make it a little more special. A pulse wave can be thought of as a switch. The switch is off. It doesn't pass any voltage. When the switch is on, it has some voltage. When the switch is off again, it goes back to 0 volts. As we activate the switch faster and faster, it starts to make a pulse sound. I'll set the oscillator frequency real low. That's our switch getting turned off, on, off, on. As we increase the frequency, the switch goes faster and faster. On the oscilloscope, we see our switch is on half of the time and off the other half. This pulse has a 50% duty cycle, which means the switch is on 50% of the waveform cycle. A 50% pulse wave is also known as a square wave. We can increase or decrease the pulse width. Notice how it makes the pulse sound fatter or thinner. The pulse usually sounds fattest when it is a square wave. If you've ever powered on an analog oscillator from sitting cold, you may have noticed the pitch is all over the place. This is called temperature drift, and it's normal for analog oscillators. Today's technology has come a long way with precise digital processor-controlled platforms. With analog oscillators, though, it's often necessary to allow 5 or 10 minutes for them to warm up and reach operating temperature, thereby giving the pitch a chance to stabilize. Digitally generated oscillators are generally not prone to temperature drift. Now, as we have seen in the introductory video, I want to control the VCO pitch using an external keyboard controller. Here I have the Arturia KeyStep Pro, but I can use any controller device that offers pitch CV output. I'll plug the pitch CV output from KeyStep and into the input labeled keyboard. Since my analog VCO has had a chance to warm up, I want to tune the oscillator, such that when I play an A on the keyboard, the oscillator pitch is also an A note. My oscilloscope has a tuning mode where it shows me the pitch of the oscillator is putting out. I'll play the middle A key. I'll adjust the fine-tuning control for getting it even closer. Now when I play up and down the keyboard, the oscillator should be able to track each note. As another example, we'll look at my 101 VCO. We have coarse and fine-tuning knobs for controlling the frequency. There's a mixer for combining waveforms into a single output. Waveforms we've seen before like pulse, sawtooth, and triangle. It offers a noise generator that sounds like, well, noise, and something called sub. This is the sub-octave generator. Usually a sub-generator will create a square wave 1 octave below the main oscillator tuning. My 101 VCO can also make a square wave that is 2 octaves below, and can really fatten up the bottom end and makes it really useful for making bass sounds. Let's plug in our keyboard to the keyboard input and make some bass lines. Wait a minute, I'm not seeing a keyboard input here. A little help? It's there. It's just called V over oct, or volts per octave. When we use the keyboard pitch CV to control a VCO, this is the standard we are using, where each change in 1 volt will result in 1 octave of pitch. All of the semitones in between are subdivided accordingly. Knowing this may not seem useful right now, but it will be when we dive into filters in the next video. have explored pulse waveforms and pulse width. When I change pulse width control, it sounds really cool. It would be really sick if we could set up something to modulate the pulse width for us. With this oscillator we can do it because it has a PWM input, and PWM means pulse width modulation. We can use another device to modulate the pulse width. Look here, another oscillator. I'm going to start out with a 50% duty cycle by setting the pulse width control in the middle. This other control is the pulse width modulation amount. Start with that set to 0. On my second oscillator, I'll turn the coarse frequency down low and plug its triangle output into the pulse width modulation input. Then turn up the PWM amount. We can increase the coarse tuning of the modulating oscillator from low frequency rates and going into audio rates. Yeah, that's what we signed up for here. There are some sweet spots in here. So I've done some sneaky stuff here. Looking at the patch chart for this, I'm actually using an oscillator as a modulator. I have used another device to control my VCO. Keeping this configuration of using another VCO to control the first VCO, supposing we wanted to modulate the frequency of the first VCO, there's an FM input jack just for that. Frequency modulation. Over here are the mode and amount controls for that. We have different FM modes because they all offer a different flavor. The low mode will allow us to make a vibrato. It will modulate the frequency just a little bit with the right settings, as long as our second VCO coarse tuning is set to a low frequency rate. The high FM mode will be more drastic, causing more frequency modulation. An exponential FM will be downright ridiculous. If we set the modulation VCO into audio rates, we can actually make the first VCO suffer dearly. This little beastie is a Pittsburgh modular DNA symbiotic waves, designed in collaboration with one of my favorite designers, Space Hardware UK. Naked Digital Synthesis, as they call it. It uses two oscillators in phase distortion synthesis. We don't really have to know what that is, but for the purposes of setting the tuning, we'll know to set the balance to hear just the first oscillator. Plug our keyboard pitch CV into the volts per octave input as usual. Try to figure out what the default settings are if you can, and as long as we can find a setting that outputs a simpler waveform, then the oscilloscope should be able to find the right tracking for pitch. When that sounds right, then I can bring in the second oscillator. It has sawtooth, triangle, square, but then has a bunch of complex wavetables in there as well. Then it has a bunch of processor types, which determine how the two oscillators will affect each other. By changing the processor type and the detune of the second oscillator, there's a whole gamut of subtle and harsh tones in here. Seems like this VCO couldn't be farther from the simple VCOs from earlier. Just know there are a lot of different VCOs out there. Both analog and digital oscillators can become very complex in function and sound. At least now you should be able to get started and experiment with a variety of different VCOs. Hope you enjoyed this video on VCO basics and it's given some insight. In my next video, we'll enter the world of filters. Thank you for watching. Be sure to like, comment, and subscribe.